So thank you very much. And that's a pity that I am not able to be here with you all there. And I'm thankful to the local organizer that gave me this opportunity to present work online. So you presented the title, then I present my colleagues. Farzan Fatullah Zade is a PhD student, soon will be a doctor in August, hopefully, in University of Sherbrooke. I am habilitated to that university and collaborate with them. And Khalifa Goita is the professor of what's called main supervisor of Farzam, and I am the co-supervisor. This research is done for University of Sherbrooke in Quebec, in Canada. So, what is importance of non-scaling? We know all that. We have measured the GRACE data, and GRACE has some limits in what's called the spatial and temporal resolution. So we cannot have it daily, for example. We cannot have it smaller spatial resolution as that. So it is very important that we try to enhance GRACE data, improve them in such a way that we create data time varying models or the terrestrial water storage for the decision maker, local decision maker. So, and the goal is that to develop the theory here and apply over Canadian prairies area. What does downscaling is? So downscaling is the process of reconstruction of the variations of values around a specific mean value. This is the definition of Becker and Brown. So it is the same thing. We have the mean values and we want to have variation around it. We want to reconstruct this. That's called downscaling. It can be done in two ways, as we all know. It's dynamical approach, dynamical approach, and statistical approach. In dynamical one, data assimilation approaches are applied to typically utilize a limited area with high resolution model driven by lateral boundary condition to drive a smaller scale information. This method needs a huge computational capacity of computer. Statistical approach, statistical relationships between the small scale and the larger scale parameters are combined and predicted in using a statistical method. And it's very straightforward, flexible, both for spatial and temporal, and also it's possible to estimate uncertainties of the model's output, and also again large data sets. But we do it different. We use a spectral combination theory. This theory was developed for the first time by Lashovec. I think he is sitting there around, my professor, Lashovec, and later was Wenzel, 1989 and 1982. This method has been successfully applied for gravity field modeling and also for geodetermination. And also I have applied this for in ghost graduometry as well when I was PhD student long ago. So we try to develop an estimator to have GRACE models and hydrological model for this, and we use their uncertainties and try to combine them spectrally. So it is a very important in our approach that the uncertainties of this global hydrological models, so that we use global land data assimilation system, are available. So this is why that we have to somehow estimate these errors. And for the GRACE case, we already have them. So later we will apply this over a small area. It's not small, a large area in Canadian prairies, and do some evaluation that I will show you later. How can we estimate the error of a GLS model? For example, there are 6 types of information in these such models: equivalent water height due to soil moisture, slow water equivalent, canopy, groundwater, and surface water and terrestrial water storage. And summation of these 5 minus TWS, this terrestrial water storage should be 0. Now I have a condition adjustment model, and we all know how to solve it. If you solve it, based on that, we can estimate a posteriori variance factor of the model too, which will have this form based on this simple adjustment model. So we have the posteriori variance factor and use it as a quality measure for the GLDAS models when we apply it for the variance covariance matrix of the measurements, which is unity, actually a unit matrix. So then we have somehow some estimates for the quality of GLDAS model based on this condition adjustment without using any a priori information, just from GLDAS model. So the important thing is that we go to a spherical harmonic domain. For GLDAS models or the hydrological model, that's simple. We perform a spherical harmonic analysis like this, down, and we can insert them back to synthesis. That's very clear, and we all know that. So I do not want to explain that much details about that, and even for the error of that. However, the situation for the error is a little bit different because we have the data here. Let me, if I can show you the pointer, data here, we have data, and the error of the data we have already estimated based on that condition adjustment model, and we determine the error of the spherical harmonics of the hydrological models, or not hydrological, terrestrial water storages from hydrological model. And to do so, we have to vectorize, actually. So vectorize this integral in this form. And when we vectorize it, we can simply apply error propagation law. And when we apply this, when we get the variance of this, the spherical harmonic coefficients of terrestrial water storage. So everything we needed, we have now. We have the coefficients of the grace, we have error of the grace, we have coefficients of GLS model, and we have the error of GLS model. That's everything is ready to make a good spectral combination. Spherical harmonics of the grace are as potential type. They have to change. They have to change to terrestrial water storage. That's very well known formula. Pavel Littman before me has presented this, and it was developed by John Waugh in 1998, and we all know that. And if we apply this, consider only the spectrum or the spherical harmonics of it, the error of the spherical harmonics of the gray can be transferred to error of the terrestrial water storage based on this spectral property. That's clear. So terrestrial water storage from grace and from GLS, error of the terrestrial water storage from GLS and grace. We have all both. So what is a spectral combination? We write an estimator in that way. As you see here, let me show you. One summation is up to infinity, contain full frequency domain, and the other one up to some extent. For example, grace up to limited degree of 16. And these are the Laplace coefficients of the equivalent water height that we have here. This relation with the spherical harmonic is very well known. Error of this equation for the degrees below n are like that. The first term is the error of the terrestrial water storage of the height from the GLS, and this one is the error from the grace, and this term is the bias of the estimator. So, and this is the error for the higher degrees than n, and this is the bias for the higher degrees. So, by assuming that these errors are independent from each other, are independent from the signal, and by taking the statistical expectation, and after that, the mean value, applying the mean value theorem over this sphere, we come to this mean square error equation. And this is what you see here down is the error degree variances of the GLS and Grace model, and this is the signal degree variance. So if we go to the next one, so this one is showing that for determining these coefficients, spectral coefficients, we have to optimize this model. So we have to take derivatives with respect to the parameters and equate them to 0 to solve them. So for the degrees below n, we use this equation. We take the derivative and then equate it to 0. And we do the same thing for the next one, but this time with respect to b. And we have a system of equations here. If we solve it, we come to these spectral parameters or spectral coefficients for the degrees below n. For higher degrees, this process is very similar, but we do not have n. Instead of n, we have a only. Then we take the derivative and minimize the mean square error based on that and solve it in that way. So then everything is ready. Oh, sorry. Everything is ready. This is the final estimator. We have a. For degrees below n, we use this formula. And for n degrees larger than n, this one for a. And for b, this is related to the Grace data actually, n smaller than n, we use this for n larger than n, which is 0, because Grace doesn't have higher frequencies than that. So what we do now, the first thing that I explained, we have to estimate the error of the GLS model based on that condition. What you see here actually is 4 maps that we have selected at different times. For example, in May 2004, November 2006, July 2000, and October 2015, just for presentation inside the paper. But good thing with the presentation is that I could make an animation and show how this error varies over the Canadian prairies actually. And as you see here, the errors are mainly over this area. And as we will show that this area has also larger terrestrial water storage. So then we go to the next one, and the estimator that we have presented actually has this root mean square error. It means that by increasing the degree, the root mean square error should increase, and it is quite normal, as by least square means that by increasing the number of data and measurement, the error should go down. So it is that, as we see, the errors up to degree 360 is around 7-8 millimeters. So for this estimator, this is a global error of the estimator. Here you will see the left side for those 4 months that we discussed in the previous figure. We have Grace data on the left and the downscaled Grace data by combining with GLS data and Bayesian spectral theory on the right. And it is smooth, as you see, for the Grace models, and for the downscaled one with the, you will see better, and you will see high frequencies that are more details. So that's what we expected to see. And here in this animation, you will observe that how this combination is done. The left side is a Grace total water storage variations or changes, now the changes in Grace, and it's GLS model, and this one is the downscaled one. Sometimes you see something in between. Is it mean value? No, it is not the mean value. It's not simple spectral weighting. It has also some filtering property also inside that. So let's see. Go to the next one. And when we estimated the terrestrial water storage, we can remove the rest of the signals from that to recover the groundwater storage variation. That's all. And this was on the right-hand side, you will see the figures that the plots over Canadian prairies for those 4 months that we mentioned. And on the left, you see how the groundwater story varies actually over Canadian periods. As I said, that this is on the right side here. Mainly, we have high values or positive values and changes. And now we go into that side, and yeah, this animation shows that how the groundwater story varies over the Canadian periods. So, how correct is it? We use 75 piezometric wells for validation. We have divided the area into 24 pieces, as you see. We have make a mosaic like that, and we named an area, is numbered the area with 1, 2, 3, 4, 5, 6, 7, and 8 areas. And these piezometric wells are somehow smoothed and averaged, and for the comparisons. And on the right-hand side, you will observe the grace downscaled one, which is the red, and the GLS one, which is green, and the blue one is the piezometric wells. And as you observe, in most of the cases, what we have done actually is closer to the groundwater, piezometric wells, groundwater story variation. So, and on the left-hand side, you will see as well for whole area, all eight zones that we have selected. So, and in all cases, you see that the combined one is closer to the test area, to the piezometric well groundwater storage. So here, Farzam, can you help me?
The results, the correlation of the groundwater results from our method was 0.8.
Okay, thank you very much. Okay, thank you very much, Farzam. Let me move on. So what is important in our estimator is that the error of spectral spherical harmonic coefficient should be determined, and it is a very time-consuming process. But you have to do it only once, but it is time-consuming. Then it's not only the spectral combination; it's not only averaging; it has some inherent filtering property inside. So there are some surface water was not actually in GLS model, then we have to ignore that part. So maybe there are some noises in the model based on because of that ignorance. And the correlation with GLS data, it could be between the different phases between the station measurements and also hydrological estimates from the and the episomatic. And good agreements with Grace could be because of this filtering and this the zoning scheme that we have selected. But we have to select the optimal size for the zones actually. So our method is optimal. It considers spectral properties of that. The uncertainties we could estimate locally was around 10 millimeter in a standard deviation, which is around the global root mean square error that we have estimated. That's logical. And here we just the resolution of the groundwater storage and the tertiary water should be around 0.25 degree by degree, and high correlation between the downscaling and the piezometric vessel confirms success of a spatial spectral combination, and it is less than 25 millimeters over the whole area. Thank you very much for your attention.
Thank you, Mehdi, for your presentation. We have time for one question for Mehdi.